Okay, so now we're going to talk about how do we go about balancing an equation, writing and balancing an equation. So, to balance an equation, what we have to do is adjust the number of atoms of each element on either side so that they're the same on both sides of the equation. All right, that is basically the aim of this type of exercise. Now, in order to do this, one thing you should never do is change the formula of the compound or the substance on either side. All right, do not do that. Do not change. In other words, do not change the subscripts in the formulas, because by changing the subscripts, you're changing basically on paper the actual substance. So that is a no-no when it comes to balancing an equation. So here are the different steps involved in balancing an equation. The first step is that you need to write a description or a word equation for the reaction. Now, let me just say that in some cases, you might get a question where you're actually given the reaction in words. So this step may have been done for you already. All right. In most cases, I would expect that to be the case. So, for example, you might be given a question where this statement is present: mercury 2 oxide decomposes to form mercury and oxygen. All right. So that is basically the reaction described in words. All right. So the next step is that you can write down the reaction in the form of an equation with the words representing the different substances. You might find that convenient to do. I normally don't do that, but you might find it, as somebody who is learning this for the first time, convenient to do so that you have something to work with for the next step. So the next step is where you write down an unbalanced equation. So basically what you're doing is trying to determine what the formulas for the reactants and the products are. All right? And of course, the reactants are written to the left of the arrow and the products are on the right of the arrow. So, in the case of the reaction, which was described in words in the previous slide, this would be the equation, which would be unbalanced. So on the left, you have the formula for the mercury 2 oxide, which is HgO. And on the right, you have the formula for mercury, which is Hg. And you have the formula for oxygen, which, remember, is one of those substances that exist in nature as a diatomic molecule. So therefore, it is O2, right? So that would be the unbalanced equation. And this equation, of course, is unbalanced because if you look at it carefully, you'll see that there's one oxygen atom represented here, but here you have two oxygen atoms. All right. So that's the unbalanced equation. And as stated here, the next step in your effort to balance the equation, you cannot change the formulas for these substances. So basically, you cannot add any subscripts to, for example, the mercury here, or the oxygen here, or the mercury here, or you can't change this 2 here. All right. So you have to just leave those subscripts as they are and move on to the next step, which is where you balance the equation. And therefore, what you're going to do at this point is that you're going to count and compare the number of atoms of each element on either side of the equation, and then you determine the elements that require balancing, and that's what we're going to do here in this case. So in this case, you'll notice that you have one mercury atom on either side, so that is okay for now. But when you compare the oxygens, you'll notice that you have one here on the left side, but 2 on the right side. So therefore, the oxygens are not balanced because you have equal or unequal numbers of oxygens on either side. All right. So therefore, we need to go about balancing the oxygen. So how do we do that? Well, we balance each element one at a time by placing coefficients in front of the formulas containing the unbalanced element. So basically, that's what we do. And the coefficient that is placed before the formula, and this is a key thing you need to remember, will multiply every atom in that formula by that coefficient. So going back to this, we want to balance the oxygens. So what we do is that we place a 2 in front of the mercury 2 oxide. All right, so now the oxygens are balanced. All right, we have 2 oxygen atoms on the reactant side, the left side, and 2 oxygen atoms on the product side, which is the right side. However, you'll notice, even though the oxygens are balanced, you'll notice that the 2 here affects not only the oxygen, but affects the mercury as well. So now we end up with a situation where we have 2 mercury atoms on the left, we have 1 mercury atom on the right. So the mercury obviously are not balanced. So what do? So the mercury is not balanced. So what do we do in this case? We basically multiply the mercury here by 2. In other words, we place a coefficient of 2 beside the mercury on the right side or the product side of the equation, and therefore we have achieved the balance of the mercury atoms. Now we have 2 mercury atoms on the left side and 2 mercury atoms on the right, so therefore the mercury atoms are now balanced. All right, so everything is now balanced, right? And normally what I tell my students is that after you think you have balanced everything, just do one final check through to make sure that everything is balanced, which is the case in this example. So as you can see here, you have 2 mercury atoms on this side, 2 mercury atoms on that side, 2 oxygen atoms on this side, 2 oxygen atoms on that side, so therefore the equation is now balanced. All right, so that's a simple example, but of course, as you can imagine, things can become a bit more complicated. So we're going to go through a couple of examples, and the first one is given here. Now in this case, they gave you a form of the equation in words. In other words, they use the words to represent the formulas for the different substances. So let me go to here, get the pen function, get the right ink. Okay, so this is the formula: sulfuric acid plus sodium hydroxide to give sodium sulfate and water. So the first thing you need to write down, of course, are the formulas for the reactants and the products. So I'm going to start with the reactants first. So the formula for sulfuric acid is H2SO4. And we know that based on what we learned in chapter 5, right? You should know by now how to write down the formulas for acids based on the corresponding anion, name of the anion. In the case of sodium hydroxide, the formula is now NaOH. Okay, so that takes care of everything on the product side, on the reactant side, I'm sorry. And then on the product side, you have sodium sulfate. Now the formula for sodium sulfate is Na2SO4, and the formula for water is, of course, H2O. If you don't know that, then that's really sad. All right. Okay, so this is the unbalanced equation, right? We have not done anything to ensure that the number of atoms of each element are the same on both sides. So let's start off by looking at the hydrogens, and you'll notice that on the left side we have 2 hydrogens here. On the right side we have 2 hydrogens. So the hydrogens are okay. Now in this particular situation, very often you'll see where a particular polyatomic ion exists as a unit on both sides, right? And what you can do is treat that unit as if it's an element itself or an atom itself. So I can look at this and say, well, I have 1 sulfate here, and on this side I have 1 sulfate here. So therefore the equation is balanced as far as the sulfate is concerned. So in other words, I don't need to separate into sulfur and oxygen when it comes to balancing that part. I could just treat the sulfate as one intact unit. Now here we have 1 sodium atom here, but here we have 2. So what I would do is put a 2 in front of the sodium here, and then as far as the oxygens are concerned, I could look at, and again, I'm not going to take into account the 4 oxygens here because I already accounted for it when I balance the sulfate. I would see that I have 2 oxygens here, all right, but I have only 1 oxygen here without the sulfate oxygen. So I would put a 2 here, all right. And then when I count up the hydrogens, again, because now the hydrogens will be unbalanced in terms of, well, it's not unbalanced now actually, but I'll count it just to make sure. You have 4 hydrogens here, you have 2 hydrogens here because of this 2 here, and then you have 2 more. So therefore now we have a completely balanced equation. So as you can see, this exercise is a kind of mixture between a kind of systematic approach, but then again, you might have some trial and error because in some cases you might have to place a coefficient in front of a formula and then erase it later on. So that's basically how we do this equation. Here's another one. Now in this case, you're given the reaction between butane, oxygen to form carbon dioxide and water. Now I wouldn't expect you to know what the formula for butane is, so I'm just going to write it down here. It is C4H10. All right, that's a formula for butane. And as we all know, oxygen exists as a diatomic molecule. The formula for carbon dioxide, of course, is CO2, And the formula for water is H2O. All right. So again, the task is to balance this. Let me create some space here. Let me get the eraser and erase part of this, make the arrow shorter so that I can place a number in front of the CO2. So, okay, so that's the unbalanced equation here. So first thing I notice, we have 4 carbons here. We have only 1 here, so I would put a 4 in front of the CO2. We have 10 hydrogens here. We have 2 here, so I put a 5 in front of the H2O. And then as far as the oxygen is concerned, I notice that we have 2 here. Here we have 4 2s 8 plus 5 13. All right. Now, this is a very interesting issue right here, because the question now becomes, how do we ensure the balance of oxygens? Because 13 is an odd number, but we have a 2 here. If you place any number here, any integer here, that would make the resulting oxygen count even, which could never balance with the 13 oxygens on the right side. So what I would do is I would put, and this might look a bit unusual, but I would put 13 over 2 here. All right? Because 13 over 2 times 2 gives you a total of 13 oxygens, and that will balance with the 13 oxygens on the right side. However, this would not be the final answer, right? Because remember, we need coefficients being integers in the final answer. So what I would do is I would take this equation and I will multiply the entire equation by 2. And the reason why I multiply by 2 is because if I multiply 13 over 2 by 2, I'll end up with 13 right here, and that takes care of converting that into an integer. However, that 2 will affect everything, right? So basically the final equation is going to be 2C4H10 plus 13O2 to give 8CO2 plus 10H2O. And I will do a final count to make sure that everything is balanced. Starting with the carbon, we have 8 carbons here. We have 8 carbons here. We have 2 times 10, 20 hydrogens. We have 10 times 2, 20 hydrogens on the right. And we have 13 times 2, 26 oxygens. And here we have 8, 2, 16 plus 10, 26 oxygens. So now we have obtained or determined the final balanced equation. All right? Okay, so that's another example of a balanced equation, how we go about balancing an equation. All right? Okay, couple of things I want to say here concerning what information we can get from a chemical equation. The meaning of the formula is dependent on the context in which the formula is used. For example, if you take the formula H2O, it can mean that we're talking about a molecule which contains 2 atoms of hydrogen and 1 atom of oxygen. We can also interpret that to mean 1 molecule of water, and so on. Now, in an equation, formulas can represent units of individual chemical entities or moles, all right? And as far as moles are concerned, well, let me talk about what happens when we're using the equation to represent things at the microscopic level. So the equation here, H2 plus Cl2 to give 2HCl, could be interpreted to mean 1 molecule of hydrogen reacts with 1 molecule of chlorine to give 2 molecules of hydrogen chloride. All right. Here's another example. Propane, which is C3H8. Let me go back to the pointer. Okay, so C3H8, which is known as propane, will react with oxygen to form carbon dioxide and water. Now, this is the balanced equation for the reaction. So you can look at it at the molecular level. So you can interpret this as 1 molecule reacting with 5 molecules of oxygen to give 3 molecules of carbon dioxide and 4 molecules of water. Each molecule of propane will contain 3 carbon atoms and 8 hydrogen atoms. Each molecule of oxygen contains, or the 5 molecules contain 10 oxygen atoms for the oxygen. And therefore, when you look at the oxygen count here and do a similar analysis over here, you'll see that for each atom, carbon, hydrogen, and oxygen, the number of atoms would be the same. We can also interpret the equation based on the mole relationships between the different substances. And we're going to talk about the mole concept later on. But for now, you can look at this in terms of the mole. 1 mole of propane will react with 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of water. So at the molar level, the coefficients in the balanced equation are the same as it is at the microscopic or molecular level. All right. And below this is showing you the fact that a balanced equation represents the conservation of mass law. If you take the mass of propane and the mass of oxygen total, and you take the mass of the products, carbon dioxide and water in this reaction, you add them up, you'll see that the masses will add up to be the same on both sides. All right, so that's the reason why we need to have a balanced equation, because the balanced equation reflects the conservation of mass law, which is always obeyed by a chemical reaction. So that's it for this chapter. So the next chapter, which is chapter 7, will be the subject of the next video. Until next time.